Welcome back to the Math Professors. If you enjoy content that can be found in any college math class, please consider liking, subscribing, and sharing. I'm Professor Van Hamlin, and we're going to cover graphing a rational function using limits. So, really, like your first chapter in calculus, we study a lot of limits. I want to put it all together and explain how to graph this particular function with everything that we learned in that very first chapter of limits. So, the first thing I recommend doing is factoring this function. So then we can investigate its properties and really kind of explain why I'm choosing certain numbers for certain limits. So we know the top factors to x minus 2, x minus 4. Those two, negative 2 times negative 4 is positive 8. Negative 2 minus negative 4 is going to be negative 6. And similarly, this is a difference of squares, so I need two things that multiply to negative 4 but add to 0. So there they are. Some of the easiest thing to first find is just like maybe two solution points of this function. And the solution points we tend to use are the intercepts because those are, zeros. So the y-intercept is when x is equal to 0. The x-intercept is when y is equal to 0. So let's find the x and y-intercept right now. So x-intercept, we know this happens when y is equal to 0. And then we'll also find the y-intercept, and that happens when x is equal to 0. Now, we know that this function, when simplifying, these x minus 2's are going to cancel. So the only spot where these two functions differ would be when x is equal to 2. And since I'm not using 2 for any of these, what I'm going to do is I'm going to use the simplified expression, which is, this piece canceling those x minus 2's. So for this one, we have 0 is equal to x minus 4 times x plus 2. And multiplying both sides by x plus 2, so 0 is going to be equal to x minus 4, adding 4 to both sides, so 4 is equal to x, or I can say x is equal to 4. So remember, this is the point for 0. X is equal to 4, y is equal to 0. Similar, if I want to find a y-intercept, y happens when x is equal to 0. So this is going to be using the simplified function, so 0 minus 4 all over 0 plus 2. So minus 4 divided by positive 2 is going to be negative 2. So y is equal to negative 2. So this gives us the point x is equal to 0. Y is equal to negative 2. Now I promise we're going to do limits here. So in order to look at a limit, what I know is that this piece right here, this x minus 2 that cancels, really represents a removable discontinuity. Because I know when I'm taking the limit as x approaches 2 of this original function, the first thing we try to do is plug in 2. And when you plug in 2, you'll notice that the numerator will be equal to 0, the denominator will be equal to 0. So when you have things of this form, this 0 over 0, kind of gives you a heads up to say, this is a removable discontinuity. I can cancel, and then I can evaluate at that particular limit. So remember, removable discontinuity, this kind of represents, some kind of hole. So who knows if the function's linear? I'm just going to do this. But this would be a removable discontinuity. So it's going to look like something like that at x is equal to 2. So when I actually find the limit as x approaches 2 of this function, what I'm really actually finding is I'm finding the y coordinate of that particular hole. This is going to be the limit as x approaches 2 of f of x. So let's find that. So the removable discontinuity is going to be when x is equal to 2. So this is when x is equal to 2. So what I'm going to do is I'm going to take the limit as x approaches 2 of f of x. So I'm going to write the original function, though we know that we're going to use the simplified function regardless, because the limit of this function is equal to the limit of its simplification. So we factor, we cancel. So this is x approaches 2 of x minus 4 all over x plus 2. And now when I plug in 2, this is going to be equal to 2 minus 4 all over 2 plus 2. So what we'll get is negative 2 over 4. which is going to be equal to negative a half. So what I'm going to have is I have a whole at x equals 2, y equals negative 1/2. Now, looking at the denominator further, because again, like this removable discontinuity means it's not in the domain of this function. So what does that look like? Well, it looks like a whole or removable discontinuity. I also know a value that's not in the domain of the function is going to be x is equal to negative 2. And what that's going to look like is we're going to have some number over 0 if I plug in positive 2. Actually, negative 2. Really, if I plug in negative 2, I'm going to have, negative 2 minus 4, I'm going to have negative 6 over 0. But the real question is, like, as I approach 0, am I approaching it from the positive side or am I approaching it from the negative side? So things that look like this are asymptotes. So what we're going to have is we're going to have a function, say, at negative 2, and I'm not sure. All I know is there's an asymptote there. So the function is either going to shoot off to negative infinity or it's going to shoot off to positive infinity. And I might not be right. It might go to positive infinity from the left and negative infinity from the right, or they might go to both to positive infinity or both go to negative infinity. We have to find their limits to really verify which one is correct. So that's what I'm going to do. I'm going to take the limit as x approaches 2 from the left. So from the negative side, I'll take the limit as x approaches 2 from the right. And then I'll see what type of infinity that I get, if it's positive or if it's negative. So what this is going to be is this will be a vertical asymptote. So we have a vertical asymptote at x is equal to negative 2. Asymptote happens when it doesn't simplify, when it doesn't cancel. So what I'm going to do is I'm going to take the limit as x approaches negative 2 of f of x. So it can be equal to, this x squared minus 6x plus 8 all over this x squared minus 4. Or I can use the simplified function because it doesn't differ here. These two functions only differ when x is equal to 2. I'm actually investigating negative 2. So this is going to be negative 2 of x minus 4 all over x plus 2. So really I'm trying to keep track of its sign because I forgot to say from what direction. Let's go from the negative side. So I'm going to come from this direction. So this is going to be equal to, below negative 3. What I do know is the top is going to negative 6. So the top is going to be, this negative number. It's approaching negative 6. And the bottom is actually approaching, I'm just going to kind of choose a number that's a little bit below negative 2, say negative 3. So negative 3 minus 2 would be negative 1. So what I know is I can see this is approaching 0 from the negative side, which really means I'm going to have a negative over a negative. So this is going to shoot off to positive infinity. So this will equal positive infinity. Now, very similarly, I can take the limit as x approaches 2 from the positive side of this function, which will simplify to this function. So this x minus 4 all over x plus 2. Again, regardless, when I plug in 2, I'm still going to get, negative 2. When I still plug in negative 2, I'm getting a negative 6. But I'm coming from above negative 2, say negative 1. So negative 1 minus 2 on the bottom is going to give us a positive number. So this is going to be 0 from the positive side. So this is going to be negative over a positive number, which is going to be equal to negative infinity. So again, what we're really taking advantage here is what we know is the limit as x approaches 0 from the negative side of 1 over x is equal to negative infinity, because this is 1 over x. So what I'm really saying is that this is approaching 1 over 0 from the negative side, so I have a positive over a negative. And very similarly, if I'm going to take the limit as x approaches 0 from the positive side of 1 over x, I know this is shooting to positive infinity. The top is 1, but I'm approaching 0 from the positive side, so positive over a positive is positive infinity. So just to try to get my notation here that might not be formalized in your calc class. So this is what I'm trying to use. Okay, so I know infinity from the, this side, a negative infinity from this side. So I have that last bit of information. Now, one more asymptote. What we're going to have is we have a horizontal asymptote. And the way you check for horizontal asymptotes is you take the limits as x goes to infinity, and you can also take the limit as x goes to negative infinity of f of x. So the limit as x approaches infinity of my f of x, you can use the original function Or you can use the simplified function. It doesn't really matter. We've been just using the simplified function over and over again. Now we have to test this. You also technically have to test this, though their answers will be identical, and I'll just explain that, why that's true. So really what we're looking at is if I have a function, if it's got an asymptote, I'll just kind of pretend it's down here. If it's got an asymptote, as I go to infinity, that's what this is going to look like. So as I'm approaching infinity, it's going to get close to the asymptote. As I'm approaching negative infinity, it might get close to the asymptote. I don't, who knows, maybe from below. So this would guarantee I have this asymptote at y is equal to b. So this is what I'm investigating. If I take the limits as we go to infinity and they end up being a value, then this is what we have here. So let's do that. So in order to find these things algebraically, what we do is we multiply top and bottom by 1 over the variable to the highest power. Another way of thinking about this is I'm really just factoring, highest power, just an x. What I'm really doing is just factoring an x out of each term. And I'd have to do the same thing over here, 1 over x over 1 over x. So, distributing to each term, this is now going to be equal to the limit as x goes to infinity of x over x. So I'm just distributing this to each term. Same thing down here. Minus 4 over x. The bottom is going to be x over x plus 2 over x. So this will be equal to the limit as x goes to infinity of 1 minus 4 over x all over 1 plus 2 over x. And the limit of the quotient is the quotient of the limit, so I can do the limit of the top over the limit of the bottom. Limit of the difference is the difference of the limit, so the limit of the first minus the limit of the second, very similar for the bottom. So what I'm doing is just taking the limit of all 4 of these terms. Well, the limit of a constant is 1. The limit of this piece right here was x gets really, really big. That's going to get really, really small, so this is going to be 0. And then similarly, this would be 1 plus 0. So this limit is going to be equal to 0. So I'm sorry, not 0, but 1 over 1, which will be equal to 1. Last, let's put it all together. So we have our axes, and we know some information. What I do know is it's got an x-intercept here, 4, 0. So 1, 2, 3, 4. It's got an x-intercept. Let's color you in blue, 4, 0. It's going to be our function. We also have a value 0, negative 2. So that's going to be down here. We have a removal discontinuity at when x is 2, y is going to be equal to negative a half. So when x is 2, y is going to be equal to negative a half. I'm going to have to put a whole point there. Pretend that's at negative a half. It's pretty close. It's, negative half-ish. I also know I have an asymptote at x equals negative 2. So let's do an asymptote here. So x equals negative 2, which is going to be it. Here, and also y is equal to 1. So asymptote at negative 2. We also have an asymptote at y equals 1, because that's what happens when I took the limit as x goes to infinity of f of x. Oh, I forgot to say, when we do this thing as well, this will simplify to this thing, and if I approach negative infinity, these two pieces will still go to 0, so it'll still get 1. So as I go this way, it's still going to have this asymptote of, this is an asymptote of y is equal to 1. That's what that represents. So, all right, now we just kind of we follow the limits for these particular asymptotes. So what I'm going to do is let's kind of investigate this left-hand limit. So I know the limit is of the function as I go to 2 from the negative side. So negative 2 from the negative side. So I'm approaching it from this way. Is shooting off into infinity. So it's going to look like this. And as I go to negative infinity, we know this is going to spit out the number 1. So this is going to go here. Now, similarly, when I'm looking at this limit, as I approach 2 from the positive side, this is equal to negative infinity. So as I approach, negative 2 from the positive side, this is going to shoot to negative infinity. It's going to cruise through that hole. And then it's also going to have this asymptote of y equals 1, so it's going to look something like this. Pretend I hit that, boom. So this is going to be our function. really just verifying that this graph indeed looks like this because of its intercepts, its limits, and then, of course, the limits with that refer to its asymptotes. So if you like the content, please consider liking, subscribing, and sharing. Thank you.